All right, so last time we left off, and we had talked about some different theorems for limits, and I'll just flip through those slides real quickly just to remind you of where we were. We had talked about these basic limits, where if we have a constant, the limit of a constant is just the constant. If we have the limit of a function x, it's just that value that the x is approaching, that value a in this case. And then we had some different theorems that did everything we would ever want them to do. So if there was a property we wanted, we had it. We had the ability to do the addition. This is called scalar multiplication. This one's addition and subtraction. The third one's multiplication. The fourth one's division. The only one that even has a restriction is the division, and that's simply because we have a denominator possibility. It can't be 0. Does everybody remember those things? And that's what allowed us, when we were looking at problems like number 1 and number 2, to simply be able to input the value into the function, because we were using these addition and subtraction, division and multiplication features that previous theorem allowed us to have. And then we had this very interesting one where we had a piecewise function defined, and we talked about if we had to find the limit of this one from both directions, we had to actually look at both pieces that applied to that particular value or were nearby that particular value. All right, so we're going to take a look now at Theorem 3.2, and these are just sort of repercussions of what Theorem 3.1 allowed. So Theorem 3.2 says that if I have a polynomial, do you guys remember what a polynomial is? Can you give me an example?
Like x squared plus
X squared plus x plus 7. That would be a polynomial. So we almost think about polynomials as sort of define them in terms of what they're not. They don't have square roots, and they don't have exponents that are negative, and they don't have variables in denominators of functions, things like that. So you often see things with powers that are what you're really looking for. You're having exponential powers that are whole numbers. Okay, so 1, 0, you could have an exponent of 0, that'd be okay. Exponents of 55 would be okay, but an exponent of 4.2, not okay. So no exponents that are actually decimals or fractions or anything like that. So that's the first one. It says that if we have a polynomial and we want to find the limit, we can simply plug the value in. In fact, we did that. That was example number 1. That was a polynomial. And we did it. We evaluated it by plugging in the value. Theorem 3.2 says that if we have a limit, that suppose we have the limit of a function is L, and we have a positive integer, then if we want the nth root of the function, and we want to take that limit, then we could take the limit of the function and then take the nth root. So equivalently, we could simply take the nth root of what the limit was to begin with. Again, this is one of those things that, like, man, I'd really like for that to be true, and we get it. It is true. It works. And again, it's a repercussion of those theorems that we had, those pieces of the theorem in Theorem 3.1. Now, there's some details right here. Let's just run through this real quick. It says if n is even, we have to assume that L is positive. So, do you know what that's talking about?
You can't take a square root of negative.
Right, so for a real good example would be that if n were 2, like a square root, we can't take a square root of a negative number, right? That becomes something that's a complex number or an imaginary number, and we're working in calculus, for the calculus you're in the real number system. So in order for this to work, if we have, and it's not just square roots, it's actually any even power root, 4th roots, 6th roots, we can't have negatives underneath those radicals and have real numbers. So if we're going to work with this particular theorem, we're going to have to be working with real numbers, which means the value underneath that radical actually has to be a positive number to make this make sense. That's all that's talking about. Okay, is this all okay? All right. We're going to do examples. And we're going to do several examples. We're going to look at some trig next. But the examples first are going to be details about these ideas of limits. Now, if you take a look at this first one, what you're going to see is that it's similar to one we've done before. It's not exactly the same, but it's very similar. Now, the problem on this one is what? What's that? The fact that the x is squared? There's not a problem with that. We've seen one of those before, and we didn't have any problem there. But there's going to be a problem on this one. There's a 0. Brooks and Jamie, you're both saying, where's there a 0? Where? In the denominator. There's going to be a 0 in the numerator too, right? But I don't really care about that one. It's the 0 in the denominator that's a problem. If I simply try to plug this number in, I'm going to get a 0 in the denominator. And in fact, that's exactly what Theorem 3.1, Part 4 says can't happen, right? if I do this process and I get a 0 in the denominator, this isn't going to work. So there's got to be some way around it, at least in general, if there's really going to be a limit. Now, it could be that there's just no way around it and this limit doesn't exist. That's a possibility. On this one, though, there is a way around it, and that's actually why I'm using these particular examples, because I want to show you what you need to try if this happens. So the first thing I want you to be aware of is that in every step of what I'm about to write, you're going to see me use the limit notation, and you need to as well. In order for the first step, that is the given problem, to be equal to the next one, we still have to have that limit notation there. So if you're going to put equals, you're going to put equals limit, because we're not done with that piece of the expression yet. What we do need to do, though, is we need to do something called factoring. And you've all factored before. I want to take a look at that denominator, and I want to try and factor it, because the denominator is what's got problems, right? So if I could somehow get that denominator to factor in such a way that it reduced this expression, that might be helpful. How does that denominator factor? Good, x plus 3 and x minus 3. Now that's not exactly anything I've got in the numerator, but it's very close. Which one of those two pieces in the denominator is the closest to the one in the numerator? At least the most helpful, I should say it that way. The x minus 3. Why is that one helpful?
You can multiply by -1.
You could. So if I took this denominator and the numerator and I were to multiply by -1, I'd have one of them change directions, right? So I'm going to actually draw that out just in case you're not following what I'm saying out loud, because it sounds a little funny, and if you haven't seen it in a while, it might not sort of register. I'm going to take the numerator, I'm going to multiply the numerator and the denominator by -1. So if I multiply the numerator by -1, this will become x minus 3, because I'm going to end up taking this piece, and I'm going to take -1 times 3 minus x. The 3 becomes negative, and the x becomes positive. But if I multiply the numerator by -1, right, this is basically what I'm doing. I need to multiply the -1 through the denominator as well. But the reality is I don't really want to multiply it through the denominator. I'm just going to write it there as a multiplication factor in the denominator. Because if I changed the direction of the x minus 3 and the 3 minus x, I'd be back in the same situation I was just in. That wouldn't be helpful. But when I change one of them, now they do exactly match, and I can reduce them and cancel them out. Now notice, I wrote that limit again, didn't I? I hope you did too. You need to. Because until you plug the number in for x, you haven't done that step of the problem. So that notation has to exist until you actually physically write 3 in place of x. So I'm going to take one more step where I'm going to write limit, and it's going to equal the step before. So this is limit as x approaches 3. Now I've got 1 over -1 times x plus 3. Now if you want to distribute that negative through here, you can. That's fine. And then put the number in for x, or you can simply put the number in for x and then distribute the negative. That's fine too. And that's how I'm going to do it. So at this point, can I put 3 in for x? Yeah, I'm not going to get a 0 in the denominator anymore, am I? No. So I can actually plug in the 0 in place of x. This is -3 plus 3. What is this limit? -1/6. And for the most part, it was all algebra. The only step that really wasn't algebra was that last plugging in step, and even that actually is algebra. It's just understanding that that limit is the ability to do that. All right, so do be careful as you're working with these. Just because you see an expression that might be able to be factored, make sure it needs to be factored before you go down that bunny trail, okay? How do you decide if it needs to be factored? Well, plug the number in first into the denominator to see if it makes a 0. If that makes the denominator 0, then you're going to factor. If it doesn't make the denominator 0, then you're done. You can actually plug the number in and move on. So check this one first. I want you to check. Plug that number into the denominator. What will the denominator be? It is 0, right? So because the denominator is 0, we do need to factor this expression. Now, unlike the last one, this one has a numerator that also needs factoring because it also is a polynomial, right? And if we're hoping to do some kind of a reducing, I need to have it in factored form as well. So let's give it a shot. Can anybody tell me how to factor that numerator? They're both x's here, right? X minus 4, x minus 1. Does that look okay? If you're struggling on remembering factoring, this would be one of those things that you should come see me, or you should go see the Success Center to talk to them about, because you're going to be using factoring a lot in this section. Okay, so if you just need a refresher on how to do that, make sure you get some help on how to do that. That's correct on top. How about the bottom? We need to factor that one as well.
X minus 4 times x plus 2.
Does that look good? Excellent. And what's even better is that you notice then there's something that matches, right? So I can reduce that piece. The x minus 4s are going to cancel. I'm going to take one more step to write the limit as x approaches 4 of what I have left. That is, I have x minus 1 over x plus 2. That's the last time I'm going to write limit, because what can I do now? I can plug the number 4 in. So this is 4 minus 1 over 4 plus 2. What does this become? 3 over 6, which is close. 1/2, right. So this limit's 1/2. Any questions on that? Okay, the next one's, yes.
On like the original,
Number 4?
yeah,
Uh-huh.
well, I guess it kind of goes for both, but would the point 3 still exist on the graph?
There would be a hole in the graph there.
Okay.
So if you were looking at a graph like in your calculator, you would it would look like it was there. It wouldn't look any different.
Yeah, since it's
But it actually, because there's no dimension to a point, so you can't actually draw it in when you see it on a picture of like a calculator screen.
Okay. So
But if
even
you were
though
drawing it back in college algebra, we would have drawn a hole when we
Right.
did it. Mhm.
So even though you can cancel out where the 0 would possibly take place, it still
Yeah.
doesn't exist. Okay.
Yeah, it's still, and so the limit exists, there's just a hole in the graph. So like visually we have something that looks like this going on, right? Where if you go from each direction at the point, like on a graphical perspective, you're still getting close to the same location. You just can't actually arrive at that point because it doesn't exist, The function value itself doesn't exist. All right, this one's a little different. What makes this different? You got some square roots. So it doesn't seem like factoring is going to work to help us out here because I've got square roots. That doesn't look like the last two problems, right? All right, so there's a trick on this, which is why I bring it up, and it's a really common trick used a lot in calculus. And you've seen it used at least one other place before, I know, because you saw it in Trig probably. You've probably seen versions of this in college algebra. Do you guys remember what the phrase conjugate means? Okay. Can somebody describe it to me?
You just change the sign.
What sign?
The plus, instead of square root of 2 plus x, or minus square root of 2, it's plus square root.
Right. So the conjugate, when we're working with an expression, you work with it sometimes when you do stuff with imaginary numbers, trying to rationalize denominators. You do it in trig also when you're trying to rationalize denominators sometimes. While it seems maybe a little bit odd, we're going to rationalize this numerator because I can't plug 0 into this denominator, right? So somehow I want to get the numerator to have an x in it so it will cancel with the x in the denominator. That's my only chance for being able to plug this in, is if that x in the denominator goes away. So I'm going to try and rationalize the numerator to see if that can work. So anytime we're seeing square roots involved, and we're going to see another case later on with some trig functions involved as well, where rationalizing things with conjugates is going to happen. Conjugates are what you're wanting to think of. So we're going to multiply the top and the bottom by the conjugate. Now, there's that limit showing back up again. On the denominator, I'm not really going to multiply these out. I'm just going to leave it in factored form. Okay? The numerator, however, I do need it to multiply out because that's where it is that my hope lies. That's where my hope is that when I'm doing this, I will end up with only an x or maybe like a 5x or something like that left. Now, the beautiful thing and the reason why we do conjugates excuse me, is because those square roots are going to go away. So when I multiply the first two terms together, what is the square root of 2 plus x times the square root of 2 plus x? That's 2 plus x. When I multiply the inside and the outside terms, I have the exact same quantity. I have the square root of 2 times the square root of 2 plus x. However, one of them's positive, in this case that's the one on the outside, and one of them's negative, the one on the inside. So I get the same quantity with different signs, which means they add to the number 0. And that's why we did it, is because I want those inner and outer terms to cancel out. That's what happens when you multiply by conjugates. You do not get inner and outer terms. But you do still get the last term. So what is negative square root of 2 times positive square root of 2? That's negative 2. And then what happens on top? The 2's cancel. Now, I don't know that I necessarily have to rewrite this step, but I'm going to do it just in case everybody, just so that everybody's on the same page of why I'm going to be able to do the last cleanup step here. So now I have that desired x on top that will reduce with the x in the denominator. What does the top become? 1. Don't forget that. It doesn't just eliminate a numerator of an expression. I do still have something there. It's the number 1. So now I have the limit as x approaches 0 of 1 over the square root of 2 plus x plus the square root of 2. Can I plug 0 in the denominator now? Sure can. I don't need a 0 in there anymore, so I'm good with that. I'm going to get 1 over square root 2 plus square root 2. So far, so good? Okay, I'm going to take my function back up here just a little bit so I have a little bit more space. What happens when I add those two pieces in the denominator together? 2 square roots of 2, right? And that should start to feel like a trig expression somehow showing up because I've got a irrational square root in the denominator. So how do I eliminate the fact that I've got a square root in the denominator? Right. If I multiply this denominator by square root of 2, then that square root of 2 in the denominator is going to become a 4, or square root of 4, which is a 2. If I do it in the denominator, I have to do it in the numerator. So I have square root of 2 in the numerator. In the denominator now I have 2, and then what's square root of 2 times square root of 2? Another 2. So I really have square root of 2 over 4. So my final limit, and again, you don't have to show every single one of these steps. I just don't know exactly what your background is, how recently that trig exposure was and stuff, so I want to make sure everybody's seeing where everything's coming from. Are we good with the square root of 2 over 4 on that one? All right. So like I said, we were going to encounter a little bit of trig today. So the first two here, theorems 3.4 says that if I have the limit of sine of x, I can just plug the a value into sine, right? And the same thing for cosine. Again, what we want to be true works, and to be honest, it works for the other 4 trig functions as well. It's just that what happens on the other 4 trig functions that don't happen here? Do you remember? Think about their graphs. There is something that is unique to all 4 of the other graphs that does not happen at all in the graphs of sine and cosine. There's asymptotes, Zach, and Brooke's up here doing this in the air too. Yeah, we have asymptotes in all of the other graphs, right? So while we could make this sort of statement about the other ones, we'd have to have sort of that condition like our rational function had when the limit exists. You know, this works when the limit exists, and it doesn't exist at all those asymptotes. But sine and cosine don't have any asymptotes, so there's nothing to be concerned with on those. This last one down here, the special trigonometric limit, we're going to use that as a given for now. There will come a time later, I don't know if it's in this semester or next, when we'll actually show you why that works. But for now, it's enough for you to know that when you take the limit of sine of x over x, as x goes to 0, that value is 1. Okay? So just put that in your memory that when you see that sort of expression, that's a fact that we're going to be using. Okay, did everybody get those written down? All right. So we're going to do a couple of examples now with limits and trig functions. All right, so the first one says the limit as x goes to 2 of sine of pi x over 2. So what am I going to do? Somebody say it so I can do it. We're going to plug it in. this is just an example of this number 1 underneath theorem 3.4. It says I can just simply plug the value in. So this is going to be sine of pi times 2 over 2. So that simplifies to pi, sine of what? Pi. And what is the sine of pi? It is 0. Okay? If you don't still have them in your memory, it might be a good thing to do before your first exam to go back and review that unit circle. Remember those trig functions for sines and cosines. It'll help you a lot. How about this next one? What are we going to do? Just plug the value in, right? Same as the last one. Nothing any different. It's even more clean because I don't even have that pi that was in that numerator before. So do you remember what the cosine of 5 pi over 6 is?
Is it 1/2?
Nope, it's the other one.
Okay.
It's square root of 3 over 2, and it's also negative because we're in quadrant 2, and in quadrant 2 the cosine values were negative. Okay. So this is sort of a refresher and evaluation of unit circle values, right? All right, let's try another one now that's going to involve a little bit more work on our part. This one actually has the limit as x approaches 0 of sine of x over 5x, which looks a lot like what? Yeah, that little special limit that I put down there and said that for now we're just going to use this as a fact. The only difference is that 5 in the denominator, right? Well, we actually have a limit theorem from earlier on in section 3, well, theorem 3.1, that says that I can write this as 1/5 times sine x over x, right? And that's a fact about numbers. But once I have it written in that form, what that allows me to do is it allows me to pull that 1/5 to the front, and that's theorem 3.1, part 1, that allows me to do that. So that I've sort of separated the 1/5 from the limit part that's that special limit that I told you about. So then this becomes 1/5 times what? 1. There's no plugging numbers in here, right? Because obviously as you're taking a look, this is not good. If I try to plug this number in, I get sine of 0, which is 0 over 0. Lots of zeros and denominators don't make any of us very happy. But this is one of those special limits that if we remember it, we just have to recognize it when it happens and recognize that sine of x over x's limit as x goes to 0 is 1, which makes my limit for this problem 1/5. How about number 10? Suggestions, what should we do?
You break apart the tangent.
Okay, how would you like to break apart the tangent?
Sine over cosine.
Excellent. So this can be written as sine x over cosine x. Look good? Then what? This is a multiplication dot. It doesn't look much like one, but... Yes, you can. This is cosine times sine over cosine. So it's equivalent to having like cosine over 1, if you will. So those cosines can cancel. Yes. And I'm going to write it one more time, too, to show that. This is the limit as x goes to 0 of the sine of x over x. And that is our special limit, which has a limit value of 1. So those trigonometric identities that you guys loved so much, and I can say that passionately because I love teaching trig and I actually really enjoy them, but I know that students don't often feel the same way. They have a reason, and you're going to be using them in calculus. So I'm actually going to post, I hadn't thought to do it, but I will get it posted out there so you have it, a refresher of all those trig function identities that you had back in trig that may come up, and so that as they come up, you'll have a reference if you want to for those. This is a pretty simple one. It's just the, or not reciprocal, the quotient identity that we used here. It's a pretty basic one, but some of the other ones might not be quite so clear to you to remember. All right, we're going to do another one that looks a little different now. So when you look at number 11, what you notice is that there are no functions written out in an algebraic equation kind of form, right? I just have this generic f of x, g of x business going on. It looks very abstract because I don't have any numbers to be able even to plug in. So let's look what it says. It says that the limit of f of x as x approaches a is 2, and the limit of g of x as x approaches a is negative 3. And the question is, what is the limit as x approaches a of f of x squared over g of x? So you may recognize what to do, but I also want you to recognize how to write it properly to justify that what you're doing is correct. What I'm going to see, or what I want to see when you do this, is to recognize that you've got a product on top, right? This is f of x times f of x, and it's a quotient on bottom, g of x. You have from theorem 3.1, the third one and the fourth one. I went too far. There it was. The third one and the fourth one, it says that if you have a limit of two functions multiplied, you can separate them to a limit of two functions with the limit on the outside of the functions, right? And down here, that if you have a limit of the two functions divided, you can separate them to the individual limits divided. Which means that as I'm taking a look at this particular one, I can change this to say the limit as x approaches a of f of x times the limit as x approaches a of f of x divided by the limit as x approaches a of g of x. Because theorem 3.1 said I can. Right? That's what allows me to do that. And the reason that it matters is because then each of these values individually, you have a value for. They were given to you up here. Right? So every value that I've sort of boxed in right now, every limit, can be replaced by a numerical value. What is the limit as f of x as x approaches a? It's 2. So everything in that first box can be replaced by the number 2. And the second box is also a 2. And then the bottom box for the g of x is a negative 3. So what is this limit? Negative 4/3. But I want to see this work right here to justify why you're allowed to simply use these numbers in these places. Okay, that shows some understanding of these different limit theorems. All right. One more example that I want you guys to, last time we were here we got into groups. And Zach, you weren't here, but everybody else was, right? Okay, so I want you to first, right now, go ahead and get with your partner real quick, okay? And I want you to take a look at this question and see if you can come up with something that makes this question work. So this question says, give an example of functions f and g such that the limit of the sum exists, but the individual limits do not. What were you looking for? How did you make your decisions about processing through what might or might not work? Where have we seen functions whose limits don't exist? There have been two types of functions where limits don't exist.
0 in the denominator.
When we had a 0 in the denominator, that's actually the one type, and then there's two things that can happen when you have a 0 in the denominator. What are they? One of them you and I were discussing. What was it before?
Well, when the point doesn't exist.
The point doesn't exist, like we had a hole in the graph, right? Okay, but the limit still existed when that one happened, right? So what's the other case where we could have a 0 in the denominator? What could happen? Brooks, you're about to draw me a picture in the arrow side. You could end up with an asymptote. So if you have an asymptote, that would be a place where you have a 0 in the denominator, often anyway, and the limit doesn't exist. And a limit really doesn't exist when you have a 0 in the denominator in that situation. So let me give you an example of one, and you guys can compare what you have written down to something like this. I'm going to suggest that we let one function be 1 over x, and visually the 1 over x graph looks like this. It's not a great picture, but you guys remember this function, right? So it has an asymptote, agreed? Yeah. And I'm going to suggest we let g of x be negative 1 over x, which is the same picture, but like this, right? It's just flipped upside down. So this is f of x, and this is g of x. And as x approaches a, and we're going to let that be 0 in this case. As x approaches that y-axis, I have an asymptote, so the limit does not exist on either function. But what happens when I add f of x and g of x together? I get 0, don't I? 1 over x plus 1 over negative x, or negative 1 over x. This is actually equal to 0. So when I take this limit of this function f of x plus g of x, I'm actually taking the limit as x approaches 0 of 0. And what is the limit of 0? It's not a trick question, I promise. It's 0, right? It's just a constant. So these individual limits did not exist. The limit of f of x as x approaches 0 did not exist. There was an asymptote. The limit of g of x as x approaches 0 did not exist. There was an asymptote. But because of the way I constructed them, when they added together, because they were negations of each other, they added to 0, and I then have a limit. Okay? I present that to you because you're going to have one similar to that. I think it's with multiplication in your homework, where you're going to think about those things in that same way. So asymptotes are a really good way to think about where things fail. When you're doing something with multiplication, you may also want to think about trig functions, as Zach suggested. It doesn't work very well for the addition, but for multiplication, it might lead you down a trail that would actually come up with something really well, too. All right.